Now we actually look at some examples from the MVP hypervisor, and this is sort of where things get interesting when you're sort of interested in, at least if you're interested in mobile focus, because the devil's really sort of in the detail here of what these front ends and back ends look like. It's and how you sort of apply them to where in the design space you choose for the different virtualization tasks you have. So storage virtualization. So on most mobile devices, you have two classes of storage available. You have internal and external storage. This is the sort of notable exception of a certain Californian fruit company, but with that's excluded, you have these two classes of storage. Now, internal storage looks a lot like just a set of NAND chips. You'll open up the device and you'll see on the PCB a NAND chip there or two. It's typically sort of somewhat restricted in capacity for both cost and power reasons, usually just a few hundred megabytes to a few gigabytes, at least today. It's where the kernel application code, some of the data resides, and things like libraries and the middleware. And that's largely managed directly by the host operating system. In fact, these NAND devices, which look a lot like memory chips rather than, let's say, disks, which operating systems are used to manage, are actually abstracted and made to look like disks using something called a flash translation layer, which is implemented in software in the internal storage. And so I brought up this sort of flash translation layer, or FTL, because it's actually kind of important in later on when understanding the performance characteristics of these devices. So there's also external storage, and this is probably very familiar if you've ever used a camera. It's basically just the SD cards that you might be using for your camera or your MP3 player. They're also used in phones for external storage. Sometimes they're like hidden in there under the battery compartment. Sometimes they're actually pluggable or some combination of the two. Here, these devices look to the operating system more like normal disks because they have this flash translation layer implemented in hardware, and they have much larger capacities. Let's say 32 gigabytes today. The scale might scale up to much larger sizes in the future. And one of the sort of key features and the reasons people have this distinction between internal and external storage is the sort of economies of semiconductor scaling. So you might release a phone at the beginning of 2012, and at the end of 2012, that same storage is maybe a third cheaper, and so you should be able to go out and actually get bigger bang for your buck, or sort of access to the same storage at a lower cost. You can do that with external storage. You just go out and you buy a new SD card at the end of 2012, and particularly if you're a phone manufacturer, or someone retailing these phones, you can easily just swap out the cards that you're supplying and offer a larger capacity then, or reduce your costs. So that's a huge advantage of this sort of external storage, which obviously you don't get with internal storage. You can't sort of, unless you're fantastic, it's sort of soldering, you can't really replace those devices which are actually on the PCB itself. Now these devices, like the external storage devices, the SD cards, they're optimized for cost. They're designed to be cheap. These are commodities. Consumers are very price sensitive. There's not too much to differentiate to any choose SD cards, so you just get the cheapest one for the capacity you're interested in. And they're optimized as a result also for the media workloads that they're intended to support. So they're things like MP3s, videos, and photo streaming, and these sort of have I/O characteristics which look like sort of large sequential reads and writes, and that's kind of interesting because that's not what the sort of workloads that an I/O virtualization backend for storage would present from a virtual machine, and we'll see this in the next few slides. Okay, so here we actually have the gory details of the I/O virtualization stack for MVP's storage, and on the right-hand side, we have a similar sort of layout. On the right-hand side is a guest and the virtual machine monitor. On the left-hand side is the host with the user space on the top and the sort of kernel beneath. And I'm not really going to go into all the details in this slide. There's like a lot to talk about and absorb. Instead, I think it'll just be useful to sort of walk through an example I/O transaction, how it makes its way across the stack, and to understand exactly which interface boundaries are being crossed while that's happening. So on the top right, you have your guest application, which might be accessing some file, reading and writing 30 bytes at address 100 within the file, offset 100, and it does so using standard libc calls, read, write, open, close, and so on. And these make their way down to the guest kernel via the system call interface there, and sort of go through the virtual file system, down through the actual file system and block layers of the kernel. And where things become interesting from a virtualization perspective is the bottom sort of gray block there, the PV block driver. And that's where we decided with this particular subsystem to draw the line. So for storage virtualization, rather than emulating, let's say, a NAND chip and providing that up to the guest, which is pretty complicated. These are like non-trivial devices. They have all kinds of modes and things like that to deal with, and command sets and so on. What we do is we actually just slice slightly higher and provide a block device driver, which the Linux kernel already has great support for, sort of plugins of this nature, and so we're able to sort of harness that. It's also sort of the right level of abstraction for being able to intercept I/O transactions and be able to batch them and send them in a sort of large sizes across from the guest to the host. So there's definite advantages from a number of perspectives for this sort of design choice. And so that's the front end of the virtualization stack. Now the VMM then facilitates communication between this front end, the component at the top left there in gray, which is where we have our storage back-end threads running, which are responsible for actually doing things like placing this I/O, which is begun in the guest in the top right, somewhere on non-volatile storage. Now, on the right, we began at the top right with sort of a file level abstraction. By the time the I/O has made its way down that stack, you're actually at the block level of abstraction, and what the guest is doing is reading and writing to a large virtual block device. And the way we realize this on the host is via just a large file, which is placed in the host file system. And that's what the storage threads at the top left there are actually doing. They're just doing reads and writes to a single file representing this virtual block device. And then the I/O makes its way all the way down the host kernel via all these layers, and then it'll arrive either on, if it's in the file systems, on the internal storage to these NAND chips, which are in the phone, or to some SD card via like the FTL. So we actually use, for our virtual block device images and these files that I was talking about, we use SD cards almost exclusively for these. And the question is why? Well, it's one of it gets back to the first slide of sort of capacity constraints. You only typically have a few gigabytes, a few hundred megabytes to a few gigabytes of storage. A lot of this may be used already by the host operating system and applications before you introduce any virtual machines. And a virtual machine itself might require perhaps a few gigabytes of storage if it's of comparable size, let's say, to the hosted. So you can't really get away with placing it on this internal storage, at least in general. On some devices, you might be able to, and looking into the future, that might be the case. But at least today, this is impractical. So you need to place the virtual machine images on these SD cards, and there are a number of sort of challenges which exist related to performance, reliability, and security, which stem from the fact that these cards aren't really designed with this use case in mind. They're designed to store your holiday snapshots. So performance-wise, the NAND chips themselves are sort of somewhat agnostic to the I/O patterns that you use to access them. I mean, they're not entirely agnostic, but the actual sort of difference between sequential and random reads and writes to a NAND chip are not as dramatic as the ones we're actually going to be seeing in the next slide. But when you place this FTL in front of the NAND chips, which is sort of taking this view of the chips as memory devices and making them look a bit more like disk devices as a sort of logically addressed block devices, you introduce potential for performance anomalies. And in fact, the FTLs that they use there are highly optimized for cost. They are just very simple microcontrollers which are present on these SD cards that you use. But they're also optimized for sequential I/O patterns because of these workloads they're designed to support. And so that wouldn't be an issue for VMs if they issued largely sequential I/O patterns. That's not the case, and we're going to actually see this in the next few slides. So here's a sort of a graph illustrating the actual performance curves for an example SD card. What you actually see here are 4 different lines corresponding to the sequential read, sequential write, random read, and random write performance. And so in the top curves which actually overlap. You actually have sequential and random reads. So you can see from reading from these SD cards, there's little difference in how you actually attempt to read from them. But when writing to them, and when you see here that the middle curve is the sequential write performance, and the bottom is the random write performance, there's a marked difference between the two. So if we, let's say, pick a particular point in the curve, let's say 2 to the 15, that corresponds to 32 kilobytes reads and writes. Again, at that point, the random and sequential reads are almost identical, but there's easily 3 or more orders of a magnitude difference between the sequential and random write performance. So that means you're going to get, and if you just look at the raw bandwidth that you get with random writes, it's close to 0. It's in probably the tens of kilobytes a second, which is certainly not sufficient to support the kinds of IOs that a virtual machine might be issuing. So our virtual machine sort of access patterns are not exactly random, but they're not sequential either. Here you have, over time, the various blocks that are accessed by a virtual machine. There's a bit of additional stuff there about the actual file system types, of which way to tell you how these blocks match up to file system objects. That's not really relevant. What's sort of interesting to see is that you don't see nice sequential patterns here. You see it sort of hopping about all over the place. In fact, we use the same SD cards to store our checkpoint images to support the suspend and resume functionality I mentioned earlier. And here you also see it sort of jumping about. There's certainly not the sort of sequentiality that you would hope for. And this can lead to very poor performance if you use these SD cards naively. That is, if you were to, let's say, place block 100 of the guest virtual machine image at location 100 in the SD card or on a file on an SD card, because you really can't sustain the desired I/O bandwidth. The other two sort of issues are reliability and security. These stem from the fact that SD cards, for compatibility reasons, are FAT formatted. They use the FAT file system, and I guess anyone who's ever who remembers the bad old days when FAT was the main sort of file system in use in your home PC, or can sort of attest to, there's certainly a lot of reliability issues there. It's not a fault-tolerant or crash-tolerant file system, and it's being used in a mobile device, which is a much more hostile environment than one of other sort of devices that you might be using it in. Particularly, you drop your phone, it crashes, or the battery dies, or the host software crashes. Even shipping phones have somewhat buggy kernel stacks, and you can lose data. And in the case of VM, not only do you just lose a little bit of data, like one of your photos from your holiday, you actually lose the entire VM potentially, if you see sort of VM image corruption. Similarly with security, the FAT file system has really no support for access control, and any sort of party who can speak to the SD card, which is pretty much, let's say on Android, any host application, even if it's a malicious application, can read and write at will to the file which is resident on the SD card. And so that's not particularly great, because it doesn't sort of, at least unless you do something clever, it doesn't really allow you to effectively isolate the virtual machine from the host operating system and applications. So to sort of address the performance reliability concerns, it's interesting to take a look at something called log structured file systems, which is where we borrow some ideas from in our VM images in our storage virtualization backends. So with log structured file systems, I guess we need to sort of go back in time to about 2 decades, and we're not interested in flash storage anymore. We're interested in spinning magnetic disks, there, the original researchers who were looking at log structured file systems found that there's this growing gap between this sort of slow seek latency. I mean, any of you who've done sort of an OS class will know that the disk access time is sort of dominated by the seek latency, where you're moving the drive head from one point in the platter to the other. So there's this growing gap between the seek latency and the CPUs, which were just getting faster. And so in order to address this, they had to invent sort of somewhat smarter file systems. So, and I'm not really, I'll talk really just about write performance here for reasons, sort of beyond the scope of this, to sort of discuss the reasons why reads weren't too important to them as well. But just suffice to say that in that particular setting, it was also the case that it was the disparity between sequential and non-sequential writes that was the real issue, and not with the reads. So their solution was, okay, so rather than when I want to write to block 100, I seek to location 100 in the disk and write there. When I want to write to block 32, I seek to disk location 32 and write there. Their solution was, well, what if every time we write, we just append to the write after the location of the previous write? And so we never seek, and there are never any non-sequential accesses. So, well, what are the implications of this? Well, first of all, you achieve your highest amount of bandwidth possible because you're always sort of writing sequentially. On the other hand, you need to sort of update and maintain metadata to let you know where block 100 lives, because it no longer lives at location 100, it might live at location 37, and you need to actually seek there when performing a read. And so, beyond just sort of performance, this is also sort of a really neat concept because it allows you to achieve sort of a certain degree of fault resiliency and crash recovery, because what you now have actually in your log is not just one value for each block, but you may have multiple copies of each block, because when I write block 100, then block 30, then block 100 again, I'll actually have 2 copies of block 100 in my log on the disk. And this means that if I have a crash while writing the second copy of block 100, I can actually go back through the log and find the last good copy of block 100 and recover in the event of a crash once I've detected this. So that's sort of a bit hand-wavy. I'll actually give a sort of a concrete example now of sort of how the logging works, because this is sort of key to how our storage backend works. So what you have here is an example where you have logical block 3 at logical at log location 0 here, and that's just the latest copy, and there are no other sort of blocks present on the file system so far. Along comes a write to logical block 0, and log location gets placed at log location 1 right after the previous block, and so on. Log location 1, logical block 1 gets placed at the next log location, which is 2, and things might become interesting now when we have 3 written again, and that gets placed at log location 3. We update the metadata to point there, and suddenly we have this old sort of stale block sitting back further in the log. And this becomes important because it's sort of a detail I haven't mentioned, and that is you can't just keep writing to this log forever. This log, you'll eventually run out of sort of empty disk space, and you need to perform garbage collection, much like you do in something like the Java heap, but you need to do this in the your actual file system to recover contiguous blocks to be able to actually continue to log when you actually run out of space. Now, we can't actually change the the file system on these phones and change the FAT formatted SD cards, because we need them to maintain them in the FAT format for compatibility reasons, and also so that you don't lose data when you install a virtual machine. You don't want to have to lose all your holiday snapshots, which are sitting there on the SD card. Instead, what we do is we structure this file, which is sitting there on the host file system, a lot like a log-structured file system. And internally, it has a log, and we just keep appending to that. And that has the effect that actually on the disk, you effectively have a log being maintained, assuming there isn't too much fragmentation on the host operating system. And that allows us to actually achieve both these sort of performance reliability goals that we're concerned with, and on the security front, it doesn't help at all. What we actually do is we make use of cryptography there, and I'm not going to go into too much into that, but just suffice to say we use like basically XTS AES encryption to provide confidentiality guarantees, and we also use integrity checksums so that even if a malicious party can read and write the contents that are sitting there on the SD card, it's not going to be able to learn anything because things are encrypted. And if it does try to modify something, we detect this via checksumming. And we maintain our checksums and our keys in some protected storage, which is subject to access controls, and the malicious party won't get to see. So that's all there is. I probably told you more than you want to know about storage virtualization, but that's all there is to it. The final sort of slide here just indicates some of the speed-ups that are achievable. If you look at the gray bars, which are the only ones which are really interesting, immediately you can see that speed-ups of anywhere from 5 to about 17 times are possible using this LBS format, this log-structured format, over what you would achieve with just like a naive virtual machine image format, which placed block 100 of the guest at location 100.